Okay, welcome back to this introductory video about Gauss's law. What I've done is I've combined the definition of flux right there with what Gauss's law says about flux, which is that it's the total charge enclosed by a surface divided by the constant epsilon naught. So now what we're going to do is we're going to exploit aspects of the integral to actually use this to very easily find the electric field for some situations where we don't have any idea how to find the electric field in other ways. Now, I don't mean in any other way. There's a complicated direct way of getting the electric field from any system using a bunch of calculus, right? But if we use some tricks to calculate this side of the integral, then we can actually pull the electric field out and just use the total charge enclosed and some of the geometry of the surface to figure out what the electric field is. So that's what we're going to do. Now, the real sort of best example of this is doing it for a sphere. So you can do all sorts of interesting spherical geometries because the integrals of spheres are pretty easy. I'm actually going to do a plate because I want to wait to do the spherical case in class because that's going to be like sort of the key example. But the plate is very nice too. So what we're going to do is we're going to take a bunch of charge that's on a plate of basically infinite thinness, so a very thin plate. So I said plate, but really what I mean is an infinite plate. So not a plate that's just like this big, but a plate which is infinite in size. And the reason we have to have it infinite in size is so that we can say enough about the electric field. So that'll be obvious, I think, once I get there. But just to be clear, I'm going to draw my plate with dotted lines to indicate that like it's not edges, like the plate goes on forever. This is physically sounds insane, but actually basically what we're doing is we're finding the electric field very close to the plate. So if we're close to the plate relative to the size of the plate, this calculation is very good. So there's my plate. You know, I drew dotted lines to make it seem like it wasn't actually the boundary. It like goes infinite, but I just want to be able to draw something, right? So I'm going to put charge on this plate. I'm going to charge it up with a charge density. So that means a charge per unit area. So this is going to have units of like Coulomb per meter squared. But all I'm really doing is I'm just putting some charge on it. I can't, put charge once every centimeter I put a charge or something, right? Whatever the density is. Okay, and the question I want to answer is what is the electric field at some point out here? And my claim is that I can use this to do it. So on the surface, that seems insane because we have to calculate the flux if we're going to use this, but I don't know what the electric field is, A, so I can't put anything there. I don't have a surface, or I'm going to have to define a surface, so I can't do anything there. The Q enclosed, okay, I could imagine figuring out how much Q is enclosed by some surface because I know the density here, but I don't know what the surface is, so it seems very difficult. So the first thing we need to do is convince ourselves that this electric field is a little bit simpler than we think it is. It can't be over here. It can't be pointed this way with some magnitude or this way with some magnitude, some other magnitude. The electric field is pointed away from the plate. And so what I'm going to do is I'm going to draw that, and then I'm going to try to convince you that that's true. And along with that, I'm going to pick a direction for the electric field. So I'm going to say that this is the z direction, and the electric field is only in the z direction. Okay, so how do I know that? Well, so imagine the following situation. I have two charges, let's say of equal magnitude. Let's say they're both positive, and I want to find the electric field, exactly in the middle of them, but like over here. And I want to find what the electric field is. Okay, so what I'm going to do is say, okay, what's the electric field from here? Well, it's positive, so it's pointed that way, so it's right there. And what's the electric field from there? Okay, well, it's positive, pointed that way, like that. The total electric field is the sum of those two vectors. So clearly the sum of those two vectors. The direction here is going to cancel with the direction there, and then you get the sum of the two vectors being something like that, right? So this total electric field is like there. Okay, how is that related to this situation? Well, notice that as long as I pick two charges that are exactly equidistant from the center line, this happens. So I could have picked them here, I could have picked them there, here, 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 anywhere. I would always get an electric field which is just pointed that way because of the cancellation of the field that comes from, in the sort of vertical direction. Well, the same thing happens here. Every electric field point here has some charge here and some charge exactly equidistant from it over there, always canceling in the parallel direction to the plate. So all those vectors are always going to cancel. If I pick one way up there and one way down there, they are still going to cancel, giving you an electric field which is only pointed in that direction. So we have an electric field which is only pointed in the z direction. So we're going to say that the electric field is some value E naught times z hat. And actually, we can do a little bit better than that. We can have some dependence on E naught. In fact, the electric field can actually depend on z. meaning that it might get bigger or smaller as you get further and further away from the plate. Now, it can't depend on whatever the other two directions are, because if you went this way and this way, it's an infinite plate. It looks the exact same. So you can't have any dependence as you go in the XY direction. But you can have some dependence in the Z direction. So that's our electric field in this situation. Okay, so how am I going to find that electric field? I claim that I can do it this way. First thing we need to do is pick a surface. Now, we want to pick a surface that appears simple, and the flux will be easy to calculate through it. So what I'm going to do is I'm going to pick a square surface, which is going to be right where the electric field is. Right, so that's one side of my surface. I'm going to go this way through the plate onto the other side, and then finish its squariness. Little hard to draw, I'm trying. Yeah, that kind of seems okay. Right, so it's a rectangle that is piercing through the plate, so that there is some part of the plate which is enclosed inside the surface, some part that's not, and some part that's not. Okay, fine. Now let's think about if we're going to actually calculate the flux of the electric field through this surface. Now, we can immediately see some things, which are you're probably seeing why I picked this particular surface. If the electric field is pointed away from the plate, the flux through the four sides of the rectangle that are perpendicular to the plate is 0. The dot product between the sides that are perpendicular to the plate, the area vector is like towards you or towards me. That's a right angle with respect to the electric field, because the electric field is in the z-hat direction. So those are not going to contribute. So we have 6 surfaces, right? 1, 2, 3, 4, 5, 6. 4 of them are 0. So 4 of them, the flux through them is 0. We only have to worry about this guy right there and this guy on the other side, A2. Those are the only fluxes we actually have to calculate. So let's write those as vectors very carefully. So this guy has some area, and I didn't really define how big the area is, so let's say it's an area of A. It's a square of area A, right? Who cares? It doesn't really matter. So it's got some area right there. The normal vector is what I'm concerned with. So the normal vector there is the same direction as the electric field, is z-hat. Cool, no problem. On this side, this area vector is going to be the same size because it's a rectangle, but its normal vector is going to be pointed in the opposite direction. So it's going to have a minus z-hat normal vector. Okay, cool. We've decided that the 4 sides are 0, so we just have to calculate the flux through those 2 sides. So this is going to look something like, and I hope this is not too complicated, but basically, it's going to be like E dot A1 plus the integral of E dot A2. Right, I'm splitting up the integral into the 2 pieces we need to do. You can do that with integrals. Okay, so the next step is to put in these explicit vectors into this calculation so that I can see what's going on with the directions, and then I'll see what's going on with the integral parts. And just to be a little bit careful, this is a differential A, so really what I should be writing, if this is the total area, the differential A is something like, z hat dA, where dA would be like your dx dy, right? So I'm not going to actually put in that dx dy because I'm not going to need it, but in principle, this area as a differential would just be the same exact thing, dA, what with the z hat in there, to indicate the normal vector. So there's the first one, just straight up copying what I have over here. I sort of dropped the dependence, but in principle, this E0 could depend on Z, right? We just know it doesn't depend on X and Y. Next one is the same thing, just being a little careful of the negative sign. So notice that when we get the electric field this way on this side, it's going to be that way on the other side because the positive charges are going to make the electric field point the other direction. So we just have to be careful about that. Put a negative sign in right there as well for the switched electric field. Okay, so that's that. Looks kind of messy, but we just have to handle the unit vector stuff, right? So z dot z, that's 1, no problem. Minus z dot minus z, okay, that might be confusing, but the 2 negative signs cancel. The z dot z then is 1 again. So actually, both of those are 1, and we get a nice expression with getting rid of the vectors out of this, this integral. Actually, 2 contributions is the same thing, so I'm eventually going to add those together, right? Okay, but now, so that's the first sort of simplification. Once you deal with the directions, you get rid of the directions. You have no cosines or anything because the normal vectors are the same direction as the electric field. That was a key part of the way that I picked my area, is to make the normal vectors of the area in the same direction as the electric field or perpendicular to them to make them zero. Now, let's think about what this integral says. This is an integral of the electric field, which might depend on z, so it might depend on how far this way you go. This is a dx dy, because this area is perpendicular to that electric field. So, in fact, this integral has nothing to do with the electric field. There's no xy component in there. There's only a z component. There's only an xy component there. There's no z component. So this guy's constant with respect to that. You can just pull it out. So in fact, what we end up with is I'm going to put a 2 here to deal with the fact we have 2 of them. And I'm also going to pull out the electric field because it depends on z, and the integral is over x and y. Okay, looks good because now we have something which looks like our electric field. That's the step we needed. We need to pull out the electric field from the integral so we could actually just calculate the integral without it. Now we have the integral over an area. That's just an area, right? If we had a dx dy and we had like 0 to a, 0 to b, whatever, we would just get the area of the surface. So awesomely, we end up with an equation. The result of the flux could not be easier. Even though we did some complicated Gauss's law stuff, it's that. It's twice the electric field times the area. Fantastic. So that's really the key thing that we need. Now I'm going to go back to our original Gauss's law equation to show you how we use that to find the electric field. Okay, so I'm going to take this guy, which is our result for here, put it in there so that we have, 2 E naught, maybe as a function of z times the area, is the total enclosed charge divided by the constant E naught. Epsilon naught, sorry. Don't want to get confused with that E naught. Okay, so what do we do now? So I think we're basically done, except we need to figure out what the enclosed charge is, right? We need to see how much charge is enclosed by the surface we created. Luckily, that's quite easy, right? We have the charge density. We always need to know something about the distribution of charges. Maybe we'll have little single points in there, but in this case, we have an actual distribution of charges across the plate. And we want to know how big that area is to know how much charge is enclosed in there, but we know how big that is. It's this area. Whatever the area was out here is the same as the area there. So what's great about this is the enclosed charge is just the density times the area. That's it, because if we have a charge density in terms of like a 2-dimensional charge density, and we know how much area is being used, we know how much charge there is inside. It's the density times the area. Cool. And now we're done. And now we see how amazing this technique is. The area cancels, right? The area is on this side because it comes from the integration of the flux. The area is on this side because it comes from the amount of charge enclosed. Those two guys cancel. Divide by 2. E naught, I'm going to write as a function of z, but actually we're going to find out it's not a function of z, is going to be sigma over 2 epsilon naught. I mean, amazing. Like, this electric field from the plate, which we started with having no idea anything about, we didn't develop it down to the fact that maybe it's directed away from the plate with some dependence on z, so maybe it got stronger or weaker as it went away from the plate. Apparently, the electric field is 100% constant. It's just the charge density on the plate divided by a constant. That's the electric field from a plate. Now, this is really remarkable. I mean, if I was going to just pick a random electric field point and say, here's a charge distribution, I would have to do some kind of insane integral to add up like all the charges on the infinite plate. And in fact, you can do that. You can do that calculation. I don't think we'll do it in this class because it's not worth it. We just did a super easy version of it using this powerful technique called Gauss's law. But again, let's just emphasize, the electric field is constant. We had no idea that it was such. We argued that it was in the z direction, and then we stuck this surface here, and we used Gauss's law as an integral of the flux and counted the charge enclosed, and we figured out that the electric field is constant, does not depend on z, does not depend on x and y, it just is this exact value. If you look up in a book that gives like a 5-page calculation about how to do this, they'll give you that 5-page calculation, and they'll get this, right? So, remarkable technique that Gauss's law allows us to do. Now, we have to be careful how we use this, because if we had like some kind of weird charge distribution that wasn't constant, it would be a challenge to find this. So we do have to be careful how we use this technique, but it's an extremely powerful tool, A, to find the electric field, And also, Gauss's law is one of the fundamental concepts in electromagnetism. This is sort of an application of it, but the idea that the total flux is equal to the charge enclosed anywhere is a key aspect of all of electromagnetism. So anyway, hope this video has been helpful and interesting. I think Gauss's law is kind of a remarkable fact of nature, but as far as an application goes, its key application is to find the electric field in situations where we would have no idea how to do it otherwise. Okay, great. Hope this has been helpful. Thanks very much, and I will see you in class.